Thank you. Firstly, thank you to everyone for being here and to Manuel and Maria for organizing this session. Well, my name is Scherezade Barquero. My thesis, the title of my thesis is the modeling, design, developing and testing of a pulsed plasma thruster for micropropulsion. I'm supervised by Mario Merino and Jaume Navarro Caballé. It's my fourth year of PhD as a member of the EP2 research group. So I'm going to present an update or a kind of summary about my thesis, but I will focus mainly on some of the results of the current ongoing experimental campaign, because I'm going to present them next week on the IPC conference, so I would like to share them with you. So firstly, I'm going to talk about the fundings, the projects that frames my thesis, and it's the Martin Lara Regional Project, and the aim of this project is to validate, to airborne validate some technologies and to target at the CubeSat mission in some years. So one of the challenges of this project is to develop a micropropulsion system for CubeSat, and this is one of the objectives of EP2. And this is the mainly objective of my thesis. So, considering these goals, we have to develop advanced numerical modeling, and we were focusing during the first part of the PhD, the first years of the PhD, on this objective. And after that, we passed to prepare the facilities of our laboratory for this specific thruster, and to develop the experimental plan and the different prototypes in order to advance towards a final engineering model in the future. As this propulsion system, as I said, we are working on 8 PPTs that are ablative pulsed plasma thrusters. And why this kind of thruster? Well, I'm going to work to talk about the working principle. What we want for having onboard propulsion on CubeSat, what we want is to have something that has has easiness for being scalable, and also we need to be constrained to a very low power budget. So with this kind of thruster, we are within these limits. Why? Because we have an absence, firstly, of moving parts. Why it works? We have 2 electrodes that extend, forming an acceleration channels that are basically these 2 in this kind of configuration. This is the one that we are working on, that is the parallel rail, and it is spaced by a propellant. The propellant is a dielectric, it's a solid propellant, and what we want is to try to find a geometrical and operational parameters, a geometrical and operational configuration with which we can break this resistance to provoke an impedance collapse and to create a current between this channel. We are going to provoke very high currents, and as it is transient, we are going to have also a magnetic field close to it. So they are going to interact, provoking an acceleration force, that is the Lorentz force, that is going to eject the plasma. Okay, so we have these advantages, as I said, and also this is very versatile because we can modify the thrust just varying the firing frequency, but there is not an absence of problems. Why? Because we have to deal with many fields, and also because the physics is not clear behind the acceleration and the generation and acceleration physical mechanism. So this is a real challenge for EP2, as this is our first time working on pulse devices. Continue with the work done up to this moment. These are basically the objectives that I mentioned at the beginning of the presentation, and at which point we are. As I mentioned before, we were working during the first 2 years in parallel to the design and and getting knowledge about the theory. We were working on modeling. Firstly, we were working on the electrical models that are more simplified. Basically, the current state of the art, and we advanced. We did a step ahead to it, and developing a fluid model. We have stopped it for the moment, and we would like to resume it in the next year, if possible. So after that, we started to develop the different designs that we proposed. And since May of the last year, we started to operate them successfully. And we were iterating along different configurations, try to identify the key aspects, and also to do a preliminary survey about the influence factors. So here we can see some of the different prototypes. This is the current one that with which the current experimental campaign is being developed with. And this is, for example, a specific diagnostic that in the conceptual design of impulsive thrust balance, specifically for this thrust that we were developing in the context of bachelor thesis during the first part of the thesis. So the preliminary campaign, the one of the past year, was focused mainly on validate ignition to identify the characteristics of the discharges. For example, here we have the main discharge that is low frequency, and also we wanted to guarantee reliability of the ignition. Why? Because with the nominal point of operation that we have, we need an external trigger in order to activate this main discharge. So this is a very conflicting aspect because we need to ensure that it works for a long operation time, a long lifetime, and that it can bear the erosion of the different modifications, and this is of the geometry, and this triggering system is so sensitive to this aspect. So this high noise is due to this triggering system, and also we were identifying another the kind of phenomena as this kind that could be reignition, and basically we were exploring the electrical curves of these charges. We also were working with another kind of diagnostics as camera. We were observing contamination patterns. Also, we were exploring at first approach the plume with Lamor probes. Basically, it was, as I said, a first approach to this chart. So now we are trying to work in a more mature campaign. And what we want is to learn about the plume shape. So we were developing a specific diagnostic for exploring the divergence of the plume with time resolution. And this is I'm going to show it later. And this is a grid, an array of probes or of independent probes. We think that we are going to obtain interesting results with them. So before to it, we wanted to explore the ion speed of the ion population of the plumes, and for it we were preparing. Sorry, I will come back to this, but I want to show this first. We were preparing a time of flight configuration, and for it we just we just have this kind of setup in which we have different probes almost aligned with the channel and separated at equidistant distance. So what we want is to measure the delays, the time delays between them, and with them trying to obtain a trend as a function of the ignition of the ignition voltage, the initial voltage of the channel. So which are the thruster? Which is the thruster with which we are working with? Is the losset one that I mentioned before, and the geometry is basically I don't know what I have here. Okay, is 4.5 centimeters and 1 centimeter gap. We are working with Teflon, and this is the triggering system I mentioned before. With this, we create a plasma seed that is going to trigger the breakdown of the main battery, because we have the energy stored in a previous stage. So going now, because of this, to the electronics, we try different configuration for the ignition system, but in this thruster we are using a capacitive one. Both circuits, the one of the ignition system and the one of the main channel, both have basically the same configuration. We have two stages. That is the electronics one, in order to charge the battery, and after that we have the plasma circuit. Inside the storing stage, we have first a converter in order to elevate the voltage. These are Cotes converter, but the specification is that they are isolated in order to have a safer electronics. With them, we are going to charge the capacitor directly at high voltage. So the electronics were kept outside. Yes, the battery of the main channel is the one that is coupled to the platform thruster, to the thruster platform, and this is because we want to minimize the initial inductance of the equivalent circuit, and the probes are placed about 30 centimeters to the channel. So with this, we have a discharge with this kind of thruster that is repeatable. This is something that is important to be taken into account in order to analyze later the plasma results of the probes that are placed into the plume. And we have a period about 2 seconds, whatever is 2 microseconds, sorry, whatever is the initial voltage of the channel. So here, what we can see is the curves that are seen by the probes. This is the probe, sorry, that is closer to the channel, and this is the second. This is the last one. So we have identified. Here we can see here the row curves in terms of voltage, and in this second plot we have the filtered ones, and also already put in terms of the ion saturation current, that this is what we are measuring. We are biasing our probes. We have an interest region. This is for 750 volts of initial voltage for the channel, and this is a representative example of the shape. We can distinguish here interest region that starts at about 3.5 microseconds from the breakdown point, and this threshold is similar for all the voltages that were tried. What we want for obtaining the ion speed measurement is to compute these delays of each peak between probes in order to obtain a velocity measurements. We have a repeatable shape for all the voltage that basically deals with two perturbations that can be understood as two ion populations. We can have more, but we are focusing on these two because these two appears on all the range. Usually we have a consistent rate between the probes in order that further probes are perturbated less and are perturbated later. An important point is that for the characterization of the first ion population, we are focusing on the lower voltages, and for the second and for the latest one. Why is this? Because at some point we don't have consistent data with this, because problems that we can mention at the end, and also because the resolution of this one is worse for the lower voltages. So with this, we were not able to identify a growing trend or a monotonic growing trend, a consistent one with the voltage, but yes, a constant value for these two populations. This corresponds to the first one, and this for the second, and we have 50 kilometers per second for the first ion population and 30 for the second with this dispersion. Despite of that we have a constant value, this is in order this is similar to other values seen in the literature. For example, with this time of flight study, we have the same values for this also for these two populations that were identified, and also they match, they fit under the idealized maxims that we can obtain with just considering a perfect acceleration in vacuum with this initial channel voltage. And also they are in order of magnitudes and similarly to real spectroscopic measurements or of other, of course, other PPTs. So if we are increasing, So if we are increasing the energy, why it is going to. In the first case, we are increasing the amount of plasma created, but not accelerating it, and in the second, they are just can be just losses. So, okay, here what we were going to talk about is about problems, but we are going to pass about it. About next steps, what we want is just because with this we can have a first estimate a very limited one about the variation of the area along the axial distance respect to the channel. But what we want is to have a more resolution about the cross plane. So we develop this array diagnostic, as I mentioned before, in which we have different probes placed along the X plane along two directions. And with this, we obtain this kind of plots in which we can see these trends in which that they are perturbated consistently as they are far from the thruster. What we want to use this data in order to apply algorithms related with computed tomography. But as we just have two directions, the code that we develop is basically based on separation of variables. And what we obtain with each probes is basically the accumulated current along this direction. And assuming that this perhaps not so much the flow, but that all the measure can contribute to the final shape of the section. So we have two projections, one in this direction, and we assume that for each cell of the mesh, we have a linear combination of multiplying of two functions. One is just a function of the x direction, and the other is of the e direction. Sorry, the x and the e direction. And with it, we were assuming Gaussians for our code, but we can extend it to other. And what we want is to for each time instant to have an image about the plume section. So concerning dissemination activities, I participated last year on in the SPC and the MPCS and a part of the doctoral meetings. And next week we are going to present these results in the IPC. In September I will start the stage abroad at the Japanese Space Exploration Agency. We were supervising PhD that work in thrust balance that I mentioned before, and other contributions to the NASTAR project, and of course to the Martin Lara meetings. And these are other activities, secondary activities. So yeah, that's all, and thank you. Sorry for